So thank you very much. So first of all, I'm not an expert, uh, and I'm just going to tell you the story of how we're progressing diamond into 3D printing with metals. And if you can imagine sort of the maturity of both our organisation and the technologies is that far. Well, maybe we've taken maybe 1.5 steps towards that. So we're just beginning. Uh, so, so this is my talk. So it's not just vacuum; it's just stuff that we want to use or been using in a synchrotron, and that's our synchrotron diamond light source in the UK, just south of Oxford. So we've been going 10 years now. So Max 4 got users coming this in the next few months. We've had users for 10 years now, so we're a bit older. We've got 30 beam lines now, and we're in a few years' time, we'll have 33 operating beam lines. And we have a whole wide range of users coming from all sorts of different industries and environments. And this is our user program. And you can see that the number of users is increasing, and also remote users is becoming much more important to us. So anyway, so what I'm going to talk about is, so there was talk about 3D printing of plastics, and then we sort of realized that, well, actually you could do metals. So metals, and at that time it was talked about laser sintering, and when you mention laser sintering in terms of ultra high vacuum applications, everyone go, oh, sintering, it's all going to be full of holes, it's going to be a disaster. So what sort of materials are available? And people were really surprised at this time. Gosh, they do all this stuff, stainless steel, titanium alloys, is there something that we could use here at Diamond for synchrotron stuff? So one of the first things we asked is, well, is it going to be any good for vacuum use? So our first tentative was we got a company to make this simple 3D part, just to see what it was like. Can you print 3D stainless steel parts, and what does it look like? And you can see, and I've got some samples with me. And you've got this sort of orange peel surface, and people were really worried. It's going to be full of holes. It's sintered. It's going to be full of holes. So you just turn the back off and you just start to polish it up, and then you think, well, there aren't any holes. Where are all these holes? It looks good. It looks like real stainless steel. So then we started to do some vacuum tests, and then we looked at outgassing rates, and it seemed to perform the same sort of stainless as stainless steel. We looked at how it performs. We looked at outgassing rates, and our vacuum group said it just looks like ordinary stainless steel. What's the problem? So let's carry on. So we started to introduce this technology to our engineers, saying, well, look, this is stuff available. Have you got any ideas of what you could do with it? And so somebody had this problem of coming up with a bifurcated connector from this point to this point with some in vacuum cabling, and it was a bit of a complicated shape. So I said, well, could we do that in stainless steel? Yeah, so we did. So we made this part in stainless steel, welded on a couple of conflat flanges. It's not topology optimization, but it was a first step, and that's actually in use. So great. So we had another issue in that we were designing some high-speed scanning slits, and we had this bracket that was going to be made of aluminium. We wanted to, and then the company quoted it, so it was going to take ages, and it was going to be cost quite a lot. So we thought, well, could we get this made in additive manufacture? It's not topology optimized. It's not the perfect solution. But we thought, well, let's just try it. And so a company could made it. So they made it in one part where traditional machining had to be in two parts. They made it over the weekend. It was actually cheaper than machining it. And we got it made in a maraging steel. So it was heavier, which for our application, because we wanted this thing going up and down. So anything that was heavy on this side would be an advantage. Great, this is quite cool. So then we start to look at other things. So this was a clamp we wanted. So we've got two mirrors that are 1.2 meters long, and we have this clamping system to get good cooling to the mirror surface. And we've had these sort of G-type clamps in the mirror system. And we looked at, we wanted to optimize that. So we wanted the center of gravity to be at the center of the mirror, so we didn't get any torsional. So we thought, well, could I make this a casting? So we got some quotes for casting, we got some quotes for machining, and then we looked at additive manufacture, and this is the G clamp that we optimized for additive manufacture. So it's got these sort of funny beveled angles, because actually this was the bed plate that we was supported on, and then so this bed plate we could make sort of 20 at a time, so that's what we did, and that's the 3D model of it. You see all these G clamps, and that's what it actually looks like in service. So this is an in-vacuum component that we bake, and then we're looking for very low levels of outgassing rates. And in hindsight, the scientists said, oh, originally it was going to be stainless steel, and that was fine, and we made all these stainless steel parts, and then he started getting worried about carbon contamination of the mirror. So we ended up gold plating these. But if it is said at the early stage, we could have made these in titanium, and then we wouldn't have had these carbon issues. But anyway, so this is a bit of a learning experience. So that's operating, it's in vacuum, and we've had no outgassing or impurity rates. Another engineer said, oh, I've got this design problem. I want to, one of our scientists wants a furnace, but the sort of current design is getting way, way too hot. So he designed this with all these, this is stainless steel with all these internal water cooling channels. So it's sort of this sort of size. And, so, I mean, he did have a problem that one of these was getting a bit too close. But again, it's this learning experience. And this is it actually in real life. And these are some of the test results. So you're going, it's going up to almost 1200 degrees C, but the outside is keeping well below our target temperature. Somebody else has said, well, I've got this detector, I've got a Kapton window, large area Kapton window, and when I collect data, these, stuff from different angles, but the Kapton window, because it's under vacuum, distorts too much, so I need some sort of support structure. And so he looked at designing this internal support structure with these ribs, but the ribs are sort of angled, so we've got one pointing this, one pointing this way, and different angles. So he did this, and that was 3D printed, and that's all working great. And then somebody said, well, we've got another, can we make a complete vacuum vessel out of aluminium? You're mad. Okay, but let's have a go. So here we go. So this is the, as you can see, this is all the support structure here. To support this is this sort of size. And this is what it looks like finished off. So it's a bit of a development work with the company. So they were quite keen to make it all look pretty so they could take it to exhibitions and stuff. And so we made 2 of these. And this is, it's got O-ring seals on it. So it's not conflat seals or anything like that. But that's where we are with that. So you see that there's some information about the build time, 60 hours, lots of tapped holes, wall thicknesses. But so far, tests are proving, so far pretty good. We're not down to, the sort of 10 to minus 5, 10 to minus 6 level. And then we started to look at other things. So here about a heat exchanger. So for monochromator crystals, so these are in vacuum, but we want to cool them with liquid nitrogen. So the traditional approach is to have some sort of copper substrate and then braze on maybe some cooling channels. Okay, so could we design this in a better way? So we came up with this idea of so liquid nitrogen feeds into here and here, and then we've got this convoluted system of internal pipework, and that's so although titanium is not as good as copper, because you're getting the liquid nitrogen so close and so evenly distributed underneath the crystal, you get significantly improved thermal conductivity and therefore less distortion of the crystal. And then, this is not perfect as a topology optimized process, but we've got the sort of fixing points of how we've got side cooling and heat exchangers and Compton shields and all this sort of kinematic mounts and stuff. And that's what it looks like. That's the finished article. So we've included. I've got the part with me. So we had 2 parts made. Well, it was only supposed to be 1, but the manufacturer made it. It didn't build properly, so they said, well, we'll build a second one for free. So then we get the raw titanium part, and then there's all the post machining to do. And of course, titanium machining titanium, it still starts sparking everywhere. So people get very excited about that. But anyway, so there's the final part, and then there's obviously welding of the pipes to liquid nitrogen. So really, what would be great would be some copper. If we could additive manufacture 3D copper parts for thermal heat transfer, that would be fantastic. So we did get some parts made. So we did some work with a university in the UK, and they did produce a copper part, which I have here. And then we said, well, cool, we build directly onto a stainless steel substrate, and then we wire it out. What if we built it straight onto a conflat flange? What if we had this conflat flange already pre-prepared, or with, some holes here, or maybe we drill them afterwards, but you can imagine, and then it's bonded on. So actually, we start with a conflat flange and we build the copper part directly. How cool is that, eh? So we built this, and so the idea is that this is obviously just cut through, but then you could feed in water or liquid nitrogen, and there could be lots of opportunities there. Our problem at the moment is we can't get fully dense copper. So we've tried with heated platons, and we've tried different mixtures of copper, but certainly that university has not got a powerful enough laser. They haven't got a proper heated platen, so we're hoping that they're going to do some more development works. But that's still, as far as we can see, from my contact so far, copper is not there yet. This was another sort of proprietary heat exchanger. This was half size that we made, and then we did some testing on. We brazed some components on and looked at. We pressure tested it and looked at the leak rate, and of course it leaks like a sieve. So it's certainly not there yet. I did make a contact with the University of Texas, and they say they have electron beam melting equipment, and they said that we'll be very happy to do some development work with you for copper, and they told me how much and how long. Thank you very much. Don't call me, I'll call you. So that that's a possibility, but it's a lot of money. So that's where we are at the moment. So Mark Stanford is still doing some work. So he's waiting for a new machine, but very interested in work with anybody on copper. I sort of digress a bit that we're interested in sample environments for synchrotrons. So we started to look at some special, well, we have done sort of furnaces for a long time. So recently we've had one made in alumina. And this is perhaps it's another half step on our topology optimization thing, in that we've got lots of these small holes going all the way through to help it to build. And then what we've done there, so that the sample, the wire goes down here, and then there's lots of viewpoints here for different detectors. There's one on the back, one on the front, and then all these slots are for the heating wires to be threaded through. And the idea that's going to go up to 1200 degrees C. Again, that's a sort of a tube that's heated up by that sample, and then you've got X-rays. So that's why the slots are all in a funny place. But we've had it made, we've built it, and now we're just in the process of building up and testing it. So what are the issues? Well, some material properties in terms of metals. There's it varies. So from our understanding, the UTS can be a bit higher. There's higher yield strength, but lower fatigue life. And of course, it's very directional. Depends on how you build. So your material properties are certainly going to vary in different dimensions. So, and then there's a shed load of process variables that how do we control those? And you can see from a manufacturing point of view, you can make millions of these. Then control of these variables is going to be critical. And as I like it, in the UK, we've got this sort of famous baker, Mary Berry, who makes these cakes on television. And my sort of scenario is that, if I made a scone, sometimes it would work and sometimes it wouldn't, and I wouldn't really know. If Mary Berry did it, she'd get very consistent results. it's controlling the process in terms of, what materials you use, how you handle it, what the temperature of your oven is, how you mix it, all that sort of stuff. And I can imagine it's very similar to this 3D printing process thing, is that if we had something that worked this week with one manufacturer, would the same article be the same if we made it in 6 months' time with a different manufacturer who's maybe, what are their parameters? So how do we get that information back about, well, you've built this, what parameters did you use? So that if we built it in 6 months' time, I could tell them what the parameters, and what parameters can you tell me, and what parameters do I need to know in order to get consistent results for next time? So that's, from my point of view, that's an issue, and I'd be very happy to get some advice on that. And then we talked about post-processing, yes. So all this stuff, the heat treatment afterwards, the post-machining, the brazing, all that polishing, all that sort of stuff is really important. And also we talked about the design. And so our issue is that you've got, in our organization, maybe we've got engineers who've gone through this manufacturing process and they're steeped in knowledge about CNC machining. They know about wire erosion, and the way they approach things, they're thinking about how can I make this in a traditional manner. And now we're starting to think, actually, don't design it how you used to think, just think completely different. And that's some people find that quite difficult to do. So sometimes maybe we're starting to look for engineers who are coming from a completely different background. It's almost a sort of, could I say it's a more arty approach? It's a much more fluid, complex, so it's almost a sort of throw away all that knowledge you had before and start completely afresh. And so that's quite an interesting approach. And so maybe some engineers find that difficult, and so some engineers might find that easier to think about in those sort of organic type of structures. So the whole area of topology optimization and how much computing power it takes up to do that sort of thing is a thing that we're starting to look at, providing some sort of design guidance. And then the whole issue of internal stresses, and when you start to build stuff and it actually fails you in manufacture, or it actually works in manufacture, but there's so many stresses inside, and how do you know, and what heat treatment do you go through, and this sort of thing. And then the issue of inspection. Well, how do you inspect something that is so, tree-like, and so the issue is, well, what tools do you need? Do you do sort of 3D scanning of stuff? Identifying what is the critical dimensions, that sort of stuff, and the whole issue of quality control. So, as I said, it's a long way, from our point of view, it's a long way to go, but we've just started to make those first few steps. So, there we are.
Oh, thank you. Big hand. Thank you so much. And what you're drawing now is a totally complete new landscape with another way of doing the design. You're also lifting the creativity. You have the issue or the urge of control the process parameters, and also the post-processing, how to solve that. But when you bring up these examples from Diamond Light Source, this really cool applications. It's really difficult applications. How do you convince your colleagues to actually go along with 3D printing?
So how do you convince them? I think that some people pick it up and think, cool, this is really exciting. And it's just a matter of opportunities that come along, and being able to think, well, I could do this. How do I come up with a solution? I could make it in a sort of traditional manner, or is there any opportunities for looking at different ways of doing things, like with 3D printing? And I think from our point of view that what's interesting is to, we talked about this parts consolidation. If you imagine a vacuum vessel when you've got hundreds of parts that are all bolted together. So if we can start to think, well, actually, if we, instead of having 3 parts that are traditionally machined and then all bolted together, then if we can make that in one part, then there could be increased stiffness. It could be reduced weight, so inertia, resonant frequency vibration can be less. There's less facing parts, so trapped volumes are less of an issue. It could be more consistency in terms of, because there's less fixings, so it could be, built in one go, and it's delivered as one part rather than we have to start assembling and think about, well, how tight do we do these bolts up and all these sort of issues. So for us, I think there's lots of exciting opportunities there, and it's just a matter of taking these sort of baby steps in doing that. So within our group, we have 55 electrical and mechanical engineers. So what we're thinking of doing is trying to identify key people within the group who become the experts, so that anything to do with topology optimization and 3D printing, they're sort of people go to and say, well, how about it? What do you think about this? And so they've got the more experience within the group to develop those processes. Anyway, I could rattle on for ages.
If you think in 20 years, just do you think it's half 3D printed components and half traditional machine components, or what's your in 20 years?
Who knows?
Who knows? You don't even dare to
No.
have a guess.
After a few pints, perhaps.
Okay, okay.
Yeah.
We'll give him a couple of pints this afternoon.
Okay, thank you.
Give him a hand. Thank you so much.